Let's have a look at some applications of Euler's formula. So exponential functions then. So we saw e to the iota theta, but of course we can go around the circle. We saw 2 pi times, we come up with the same solution. So therefore that means e to the iota theta plus multiples of 2 pi I would also be the same number, and that would then be cos theta plus 2 pi k, I sine theta 2 pi k. Now we know that will be the same as cos theta plus I sine theta, because we've gone around the circle, complete revolution, as long as k is an integer, because we have to have whole number multiples of 2 pi. And so that therefore is equal to e to the iota theta. So therefore what we're basically saying is e to the I outside of theta plus multiples of 2 pi k is the same as just e to the iota theta. So what's that telling us? That's telling us that e to the power of some complex number z is a periodic function, and that period would be 2 pi I. It repeats every 2 pi I. Trig functions then. So remember these identities we saw before, that z to the power of n plus 1 on z to the power of n, that's always going to be 2 cos n theta. And when we subtract, so z to n minus 1 on zn, that's always 2i sine n theta. So if I play around with these, I can get, well, 2 cos n theta then, if I now turn the z to the power of n and the 1 on z to the power of n into Euler's formula, we get e to the I pi n plus e to the minus I pi n. Divide both sides by 2, I now have a result for cos n theta. So cos n theta is a half of e to the I pi n plus e to the minus I pi n. Similarly, I can play around with the sine one, and we get sine n theta would be 1 on 2i times e to the I pi, etc., etc. Alright, let's prove them then. So we're going to prove the good old Pythagorean trig identity of sine squared plus cos squared is 1. So sine squared plus cos squared, well, sine squared I can now write as 1 on 2i squared e to the iota theta minus e to the minus iota theta squared, plus for cos squared becomes 1 on 2 squared e to the iota theta plus e to the minus iota theta squared. Okay, 2i squared is 4, and 2 squared is also 4 as well. Oh, actually 2i squared is minus 4, isn't it? Yeah. So, but I've left the minus in the parentheses, taken out the common factor of a quarter, and then expanded out our perfect squares. We now get some cancelling because of that I squared. What do we got? The e to the 2i theta cancels, and so does the e to the minus 2i. So the exponential goes away. I get a quarter of 4, which is 1. Thus proving our trig identity, sine squared plus cos squared is 1. Well, let's try this one then. Let's be a little bit more ambitious. Sine cubed theta, 3/4 sine theta minus 1/4 sine 3 theta. So sine cubed, let's expand out e to the iota theta minus e to the minus iota theta all over 2i, cube it. Remember that pattern, 1, 3, 3, 1. And the denominator will become 2i cubed, which is minus 8i. Now, what have we got on top? I can now rearrange this. I want 2i on the bottom, because remember the identity with sine n theta always had 1 on 2i out the front. So I factorised out the quarter. That leaves me with the 2i on the bottom, and then on the top I've grouped the ones where the coefficient, or the size of the coefficient are the same. So the ones with 3, so I get e to the iota theta minus e to the minus iota theta, and then the one that just has a coefficient of 1, e to the 3 iota theta minus e to the minus 3 iota theta, and now I can convert those back, and we get 3/4 sine theta minus 1/4 sine 3 theta. So to prove the first one, sine squared plus cos squared is 1. Maybe a bit of overkill to use this to do that, but for something like this, that's certainly, I think, a bit quicker than other methods. Okay, what about this good old one? Products to sums. 2 sine alpha cos beta, sine alpha plus beta, plus sine alpha minus beta. All right, strap yourself in. Okay, so 2 sine alpha cos beta. Well, the sine alpha becomes e to the iota, oh, in this case it's alpha, minus e to the minus iota alpha over 2i. And then the cos beta, e to the iota beta, plus e to the minus iota beta over 2. Again, I'm going to create this denominator of 2i, because you notice the results are both signs, so I want 2i on the bottom, which is handy here because the other 2's cancel, leaving with just 2i on the bottom, so I don't really have to do anything for that one. And again, grouping things cleverly, I've got e to the I alpha plus beta, plus e to the I alpha minus beta, minus e to the minus I alpha minus beta, minus e to the minus I alpha plus beta. But then I'll split those into two things where it's alpha plus beta in both powers and alpha minus beta in both powers, and you'll hopefully notice that we've got our sign result. Roots of complex numbers. So let's find the square root of 1 minus root 3i. So yet another way of finding the roots of complex numbers. So z squared is 1 minus root 3i. Put that into exponential form, we get 2e to the minus I pi on 3. So therefore z will be the square root of 2e to the minus I pi on 6 plus pi k. Remember we said e to the I pi on 3 is the same as minus I pi on 3 plus multiples of 2 pi k. That's multiples of 2 pi. But I'm then dividing the power by 2, because I'm finding the square root. So the minus I pi on 3 becomes minus I pi on 6, and the 2 pi k becomes pi k. I want two solutions, so 0 and 1, and we have root 2 e to the minus I pi 6, root 2 e to the 5 I pi on 6. Let's put them back into Cartesian form, and fortunately they're exact values. So we can find the sine of pi on 6 and the cosine of pi on 6. And there's our beautiful answer. Root 6 on 2 minus root 2 on 2i, and minus root 6 on 2 plus a half I. Eh? No, it should be root 2 on 2i, shouldn't it? Yeah. 3e.
That's all the complex numbers.